This is our water potential paper slide video by Asia, Demaya, and Zach. The goal of this video is to teach how to find water potential and then apply it to several scenarios. Also, we'll be discussing osmosis. The water potential formula is psi equals psi s plus psi p. The psi p stands for the potential pressure. Most of the time it will be zero if it's in an open environment like an open beaker. In order to find psi s or solute potential, you must use the formula of psi equals negative I CRT. I is the ionization constant, C is the molar concentration, R is the pressure constant that will always be 0.0831. Finally, T is the temperature. The temperature will always be in kelvins. To find kelvins, you must add 270 degrees to your Celsius. I will always be the breakdown of elements unless it's a sugar, which will always end in O's, and sugar's ionization constant typically is 1.
Water always moves from a high water potential to a low water potential. If the water potential is higher inside the cell, then the water will move out of the cell. Isotonic is when the cell has equal solute and equal water. Hypertonic is when a cell has more solute and less water. And finally, hypotonic is when a cell has more water and less solute.
At 21 degrees Celsius, a cell containing 0.6 molar solution of CaCl2 has a pressure potential of 3 bars. It is placed into an open beaker containing 0.4 molar solution of sucrose at 20 degrees Celsius. Which way will water move? Okay, you have to remember that water potential equals the pressure potential plus the solute potential. So to find the water potential of the cell, you must add the pressure potential, which is 3 bars, plus the formula of negative I CRT. So the ionization constant is 3 because CaCl2 has 3 elements, times the concentration, which is 0.6, times 0.0831, which you're going to use for every water potential problem, times Celsius plus 273, which will be 294, which will give you negative 40.98 for your water potential of the cell. Now you're going to do the same thing for the water potential of the solution, but because it's an open beaker, the pressure potential is going to be 0. So when you do this plus your negative ICRT, you get negative 9.74. Water will move into the cell because negative 40.98 is less than negative 9.74. A red blood cell has a pressure potential of 5 and a solute potential of negative 3. The cell is placed into a solution of pure water. In what direction will the water move? Okay, so the water potential of the cell is going to be the pressure, which is 5, plus the solute potential, which is negative 3, which will give you 2. And the water potential of the solution is going to be 0 because the water potential of pure water is always 0. Water will move out of the cell because 0 is less than 2. A cell containing 0.8 molar solution of NaCl at 20 degrees Celsius has a pressure potential of 2 bars. The cell is at equilibrium with the surrounding solution. What is the water potential of the solution? Because the solution is at equilibrium with the cell, the water potential of the cell is going to equal the water potential of the solution. So in order to find the water potential of the solution, you have to find the water potential of the cell. So you're going to add the 2, which is your pressure, plus your negative ICRT value, which will give you negative 36.96, which means the water potential of the solution is negative 36.96. A potato root has a pressure potential of 5 bars and a solute potential of negative 1.5. It is placed into a solution that has a pressure potential of 4 bars and a solute potential of negative 3. In which direction will the water move? The water potential of the cell is going to be the pressure, which is 5 bars, plus the solute potential, which is negative 1.5 bars, which will give you 3.5. The water potential of the solution is going to be the pressure, which is 4 bars, plus the solute potential, which is negative 3, to give you 1. The water will move out of the cell because 1 is less than 3.5. In a hypotonic solution, plant cells will take up water because the cell wall will prevent it from bursting and the cell will become turgid. In animal cells, they will eventually burst because the cell is taking up so much water. You should now be able to understand what water potential is and how to calculate it and apply it to different scenarios. Thanks for watching.